is equal to 0. So just in one step you can get the force in this member. Any other force? No. So how much is FFG? No calculator?
Let's go. Calculate by sine or cosine?
Cosine.
Cosine.
This is G.
The book is wrong.
Whatever. I don't know about the book.
Yes, it's 7.82. 7.82.
ضرب 6 غلط.
7.8.
Oh no.
83 yeah. نفس طلع المومنت.
بس هو طلع
هو
بالساين.
طلع المومنت.
هو اخذ الساين ما اخذ الكوساين.
كوساين عاد 21 على كوساين 26 ضرب هون.
minus 1.8.
أخذهم دي.
The angle would be 1.5. This is 3. How much is the answer?
7.8.
So it's the same in the book.
But they take sine.
Sign is wrong.
Sine is wrong, yeah?
Yeah. Because if you use sign here, you will get different answer. If you
We
put
also
sign,
multiplied with 6, not 3,
Multiply by 6.
which is
Like,
wrong because the distance is 3.
forget about that. See it here.
Here it could be different.
What is FFG?
7.8.
7.8.
Minus or plus?
Minus.
So it will be compression. Okay, so now we have force FFG. What else? What else we need?
We take
Summation of phi.
moment of C.
Summation of phi.
You know, now we have two ways. The one way we can solve the joint F. You can combine the method of joint and method of sections together. Now if you solve, now at joint F, how many unknowns you have? Two. FFE and FFD. But we need the force in which member FDG. We need the force in which member.
Take moment C.
What
Hold on, hold on.
Sigma F1.
We can take the moment at point C. That's the one way. Another way we can solve the joint with joint. Joint F and then joint D, but it will be a lengthier procedure. Now you have the force in joint in FFG, so you have two unknown. You can solve this joint F and you can find the forces in these two members. And then again you come here and then you solve this joint. It will be a very lengthier procedure. So why not to take moment at point C? Is it fine?
Yes.
Let's take moment at point C. So if you take moment at point C, FDC will become 0.
FGG cosine is 0.
No,
Yes, cosine 0.
we should get the angle.
How much is this angle? 45?
No, 56. No, 56. We have the distance for.
Yeah. Now you have the
All
4.5. So 56 degree?
Yes, 56.3.
Now let's take moment at point C. Sigma moment at point C is equal to 0. So this 2 kilonewton, it will be clockwise?
Clockwise, yeah.
Yeah.
Minus 2.
Minus 2 into 3,
Yeah.
7. It will be counterclockwise.
6.
7 to 6.
And what about the horizontal component? It will be 0. The vertical component it will be producing which moment?
Counterclockwise.
Count as a positive.
Yes. Yeah.
F dg sine 56.3 into 3. And now there will be two components of this force, FFG.
Yeah.
So one component will produce, both components will produce
Counterclockwise.
counterclockwise. So you can take plus FFG cosine 26.6 into 3
Yeah.
plus FFG sine
26.6 into 3.
now put here FFG value negative 7.83 what you have.
Because we take it as
Yeah,
yeah.
even.
So now you have only one unknown and that is FDG. Put the value of FFG minus 7.83 and solve this equation. You will get FDG.
One point nine is 1.79.
I'm sorry. Sorry?
1.79.
1.79. Did you solve it? Is it correct? 1.79.
Minus, right?
Plus or minus?
Plus.
I don't know.
Should be minus. It's minus 1.6.
Minus 1.79. I can say 1.8.
1.8.
That's all. So you have solved this truss. You have solved not the full truss but the two members. And if you have to find the forces in these two members by the method of joints, what you will do? Which joint will be solved at first? In the method of joints, there are more chances of mistake, you know. Why?
Very difficult. You have to show it.
You guys give a force. First we
Sometimes-
will solve joint E.
Yeah. Sometimes members are zero in one joint, and then you get like a value of.
Even if you do a mistake in one joint,
It will be destroyed.
it will be distributed to the whole truss. So be very careful. The method of joints seems easier, but like at joint D, there will be how many forces?
Four.
Four.
Five. Sorry, four. Five.
And two for the five.
At joint D, there will be five forces.
Yes, with the two.
One known and
And then you have to find the sigma fx, the whole vertical component, the summation, and the horizontal. So it becomes very. And what about the member G? See member G.
Yes.
There will be four forces with the horizontal components.
five.
Fifth is the vertical.
Perfect.
So the five vertical components and the four horizontal components. So it becomes very lengthy. Do you have any other question? Okay, next is what? In this case, if you have to find out the force in member JC or BC at G, the procedure will be perfectly similar. There will be no difference at all. Okay? but just the shape of this truss is like a compound truss. A truss inside a truss. Like this. Well, still I will call it as a truss. Many of the trusses, how to decide the members or the assembly of trusses? Do you know this?
This is symmetric.
It is symmetric, but I mean, how to decide what type of truss you want to use? Do you understand what I'm saying?
Yeah.
How to decide what type of truss you want to use?
Yeah, depending on
I mean, why I have to make such a complex truss? Why?
Because we have
What's the forces? The vertical forces.
Well, it's highly debatable, but the best way you have to see, you have to see for what purpose you want to use your truss. If you want to use your truss for flat roof, will you use this truss?
Yes.
You want to use your truss for a flat roof.
No, it must be flat as well.
And if you see in this case, the slope is very high.
This is for
Yeah.
bridge.
Even not for the bridges, such high slope trusses are not used for the bridges. Well, this is the application. If you need very high space in the center, very high clear height, so the shape of truss is determined by the use, for what use you are going to place that truss. Trusses are, what do you think? Do you prefer truss on a concrete structure?
No.
Why?
Too many components.
Too many components, but it's light in weight. If you think, it's very light. Can you use this truss for 3-story building?
No. Cannot take a look.
The trusses are mostly used for the roofing.
Yeah.
Because it's light.
Like if you want to have like 6-story building, steel building, can you provide 6 trusses at 6 levels?
The shape is.
No, because they will resist the air, which would be a problem.
So it means that you can just provide these trusses at the roof level. You cannot provide at the intermediate floors.
Yeah.
So that is the one of the limitations. The other limitation, for example, if you want to have a flat roof, all these are the roofs with high slopes. So it's taking a lot of energy this time.
Let me,
No, it's fine. It's good. Well, I have designed many trusses during my professional work experience, but we try to avoid trusses. Most of the time, we try to provide either one straight beam. For example, if you provide one straight beam from the top to this point and from the top to this point, I think it will become much easier. And like this.
I couldn't hear you. Please help.
Your friend? Okay. So, see, this is just,
Answer your question.
maybe it will help you during the exam, I think. Okay, so sometimes we provide such members. I have recently done one study, and that study has compared between trusses and between buildings. That study, if you go and search, like call such structures conventional structures. Conventional means the most of the time which people have used.
Common.
But now the people or the contractors or the builders, they are moving towards pre-engineered building technology. Like this truss, if you have to make this truss, it will be very difficult to connect all these members and these joints.
Yeah.
And if it's a welded truss, again it becomes very lengthy, very difficult. So what we do, we provide like one beam, a long beam like this. Two long beams, and we join them together. Let me show you.
Doctor,
Yes.
the 1 kilonewton coming from where? 1 kilonewton, 1 kilonewton.
I mean, this 1 kilonewton, I'm not sure, but this is just the application. 1 kilonewton, how the force on this truss is coming. For example, if you want to calculate the force here, it will be the load, the reaction of the purlin. And usually we provide purlin at a spacing of 1.5 meter. Okay, let's do one calculation. For example, if you want to apply the load on a truss and you have purlins, let me go back. Where is the purlin? Here.
The joints, big joints.
This is a purlin. This purlin is resting here. Okay. So if this spacing is 1.5 meter, and the dead load of the sheeting, is, let's suppose 0.5, and this spacing is like 6 meter.
Into 6. We multiply that 6. It will be kilonewton per meter.
That will be the reaction of purlin. Okay. This distance half multiplied by length multiplied by the force per unit area, that is the total load. Divided by 2 is the reaction on each side. So how much is the value?
.675.
So this is how you get the force on the truss.
Just consider this, and also you have to consider the
Live load. This is just the dead load, self-weight, live load, wind load, and if there is snow, you have to consider snow load. Okay. What is next? Next are the complex trusses. We are not going to solve these complex trusses. Rather, I would, if you want to solve, there is one example in your book, you can do that. I would prefer to solve space trusses. So in our next class, we will study the space trusses. Okay? Because that is more important. These complex trusses have very limited application. Very, very limited application. So what about these space truss? Can you see?
Yeah.
It's a space truss. Space truss. Any other example of space truss? Maybe no. Stadium, yes.
Stadiums, arenas.
What else?
steel tower for
What about your electricity poles?
Oh, yeah.
What are these structures?
Something like this.
They are the space trusses. What about the mobile STC, then these towers? They are what type of structures?
Space structure.
Space structures. Like this, you can. It is one joint of a space structure. So next time I will tell you, but let me show you that study which I have recently done, and it's in the process. Where is that? I think I have recently submitted, and I have to open this through my email account. Let me show you. I mean, in that study that was done by my students, senior design students. So I have optimized the different trusses. So what I did, first, the student they choose a truss of their own choice, and then they reduce the height of the truss, and then compared. Now the load is same, but they are reducing the height. Do you understand?
Yes.
So, and then they found the weight. All down.
So teacher, the angle itself.
Just 1 minute. Yes, one. Let me show you this. Maybe I think it's. I mean, it is still in the process. I hope it will be published very soon. Steel is my very heart favorite area of research. I really like steel design, steel construction, and you can find many literature relevant to the steel construction, which has been the studies which has been conducted by me. I mean, if you go there, like how my main target is to reduce the weight to or to optimize the structure. Like this is one study. Soon it will be published. Yeah, like this. Can you see? I just told you some time before. This is one conventional steel building. This is PEB, but I did a lot of study on PEB. I think you can find a lot of literature which is relevant to the pre-engineered building, and it is by me. I'll show you if we have time. But what we did in this study, for example, this is a truss. If you see here, the height is 2.75 meter. Yeah, the height is 2.75 meter, and the panel length is like 1.5 meter. This is a real truss. The total span is 33 meter. The height of truss is 2.75 meter, and the center to center spacing of the truss is 6.5 meter. The parallel spacing is 1.5 meter. There are so many parameters on that. Well, so what we did, we keep everything constant and we change the height of the truss from 2.75 to this is the whole truss which is modeled in the computer. The force is like 9 kilonewton is the live load. Yes, here. Now if you see that for the same truss, if the height is 0.5 meter, the weight is somewhere 5 ton, 5,000 kg. And as I am reducing the height, I am increasing the height, the weight is reducing. So again, after this point, now the weight again started increasing. So for that truss, you can decide that which one is the optimum height.
1.75.
1.5 or 1.75.
1.5 because it will cost less.
Out of these two, you can check any height. Do you understand? It is the practical point of view. You want to do this, you want to do this construction. The work did not stop here, it continues. This is the deflection. For example, there are two things. One is the weight and other is deflection. If you increase the truss, if you if you reduce the truss height, the deflection will increase. So you cannot use these two values. But for all other cases, it's same. And then this is height, yes. And in this case, now what I did, I changed the hot rod section with the tubes. I mean, you have I section here. This is the I section. Many people use this for the trusses, but what I did, I replaced this I section with the tube. HSS being hot rolled hollow steel tube. So again, now the weight further reduced. Okay. And then, now what I did, instead of providing the steel column, I provided the truss columns. I further tried to optimize the weight. And then this truss assembly with all these parameters, these are the weights and sway, and then that was a full model of the final truss. So that is a kind of optimum truss design. This study is mainly the optimum design of truss sections. So this is about the steel trusses, but if you want to see some study relevant to pre-engineered steel buildings, if you particularly write with my name, this is the one. Minimum, many people requested me to give this document, but I did not. I will give them someday. Minimum weight design of pre-engineered steel structures. This study was also by me and by Mr. Hisham and my teacher. Many people, they have asked me to provide this study, but till now I did not, because it's a little bit, what should I say? Minimum weight design of pre-engineered steel building. And some more studies relevant to it is, this one. Design solutions for sustainable construction of pre-engineered steel buildings. It is an open access, you can find this study. In this study, I did a lot of work on pre-engineered steel buildings. Okay, so I think I should stop here. Maybe next time I will start with the design of trusses. Thank you for your time.